Okay, I'm going to tell you about a paper that is recently published in the Astrophysical Journal called Rings and Radio Waves in the Disk of the Milky Way. And the first author of this paper is Xu Yan, who is at the National Astronomical Observatory in China in Beijing. And she did all the heavy lifting and made all of the plots in the paper. So I wanted to give credit to her. So I'm going to try not to be too long in this, but in case you fall asleep before the end, what I want you to know is we identify an asymmetry in disk stars that oscillates from the north of the galactic plane to the south, to the north, to the south again, and that gives us the corrugated Milky Way, which is got a silly picture at the top, which gives you the idea of what it is. So that's the result, and in the next few minutes, I hope that I convince you how it is that we know that. So the first thing I need to do is teach you a little bit of astronomy, not very much, but just a little bit. This is a picture of a globular cluster. You can find 100 of these in the Milky Way Galaxy. There are 100,000 stars in each of these globular clusters, something like that. And if I picked up every single one of the stars, or just a sample of the stars in this cluster, and I put them on this plot, and on the x-axis I put the temperature of the star, and on the y-axis I put how bright the star is, a log scale, but it's how bright the star is. And you'll find that stars are not just scattered anywhere in this diagram. There are certain combinations of how bright the star is and what the temperature is that are allowed. And in fact, most of the stars are here on what we call the main sequence. There are a few stars that are other places, but most of them are right there. And that's going to be important for understanding this result. Now, a globular cluster, all of the stars in that cluster were formed at about the same time, from about the same kind of material, and they're about the same distance away from us in the galaxy. And if the stars were not all at the same distance, then the brightness that we see when we look up will depend on two things. It'll depend on how bright the star is intrinsically, and it'll also depend on how far away that star is. And so you can imagine that if you looked out at a bunch of stars that were not all in one globular cluster, they were just out in the galaxy somewhere, you would see stars that mostly were on this main sequence, but this main sequence might be higher up if they're closer to us, or it might be farther down if they're farther away, and then they would appear to be dimmer. Okay, because this is dimmer and brighter. All right, that's the thing you need to know from astronomy. Now I want to show you a diagram that we made in 2002 of the stars that are looking kind of this way in the disk. So it's near the disk of the galaxy, but not exactly in the disk. We're looking a little bit over the disk. And in this diagram, you can see that there is what looks like maybe a main sequence. We're not going to pay too much attention to that side of the diagram. Won't worry about that. Just look at this side. You see what looks like a main sequence over here, and then it looks like there's a whole bunch of stars at a lot of different distances up there. And so we might look at that and say, okay, this looks like we're seeing stars in the disk, right, that are all spread at different distances. But here, we saw there were stars that looked like they were all at the same distance, and it was about out here, out farther than we thought the disk was. And we saw that around at different angles around the Milky Way. And so we thought that we found a ring of stars around the Milky Way, and it's come to be known as the Monoceros ring. And here is a picture that is an artist's conception of what that ring might look like, that you have a spiral galaxy, the disk of the galaxy has these spiral arms, and then around that there's this ring of stars that we didn't know how that got there. Okay, now I'm going to flip forward to today, what we're doing with the data now. We have a lot more data than we used to have. What we've done here is taken a picture of the whole sky 40,000 square degrees, every direction of the sky that you can see, any direction from the Earth, and we flattened the sky out in 2 dimensions into a big rectangle. Okay, so this is the plane of the Milky Way, so that's where all the spiral arms are. We're seeing it, edge on. And the black lines show you where the Sloan Digital Sky Survey has imaged the sky. It's imaged the sky in all these little places. And in particular, I want you to look at these 5 stripes of data here that go through the galactic plane, because I'm going to show you those in a little bit more detail. So what we're imagining is we take this imaging data from the Sloan Digital Sky Survey, and we cut out little 2.5 degree by 2.5 degree pieces of this, and we're going to make that same color versus magnitude, color versus brightness plot for each of these pieces of the sky. I want you to get that picture in your mind, because the next frame is going to be a lot of diagrams. Okay? You're going to take each of those little things, and I'm going to make a magnitude or a brightness versus temperature diagram for each of them, and this is what you get. Okay? A lot of information on this page, but this is all of the pieces that are above the galactic plane, so we call it to the north, and this is 10 degrees away from the galactic plane, 12.5, 15, 17, is to 30 degrees. This is going up from the plane as you go down the page. And each of these diagrams has the same kind of features we saw in the original one. There are a smeared out bunch of stars here, what looks like kind of a gap, and then the monocerous ring. It's smeared out, kind of a gap, monocerous ring. Doesn't really matter where you are, smeared out, gap, monocerous ring. If you go near the plane, there's a lot of extinction. The light gets absorbed by gas and dust, and so you don't really see the monocerous ring. But as soon as you go even a little bit away, you start to see the monocerous ring. Same structure in all of these pictures. Now I'm going to show you the same plot for the data that was taken below the galactic plane in the south. And here we have a similar kind of thing. You have, well, let's look at this one. You have stars that are spread at all different magnitudes, so we're imagining that it's main sequences that are at all different distances. So something that looks like the disk, and then a gap, and then something at the same distance. And this one has usually called the Triangulum Andromeda ring, or the Triangulum Andromeda stream in the south, but there's a little bit of confusion in the literature. Sometimes it's called monocerous. But you can see that there's stars at one distance, a gap, and what looks like the disk. Stars at one distance, a gap, which looks like the disk. Because this one is fainter than the monocerous ring on the north, we lose it more quickly as we go towards the galactic plane. Again, this is 10 degrees below the plane to 30 degrees below the plane. But pretty much wherever you look, same kind of deal. Now I'm going to do a trick in the computer, which is to take all of these diagrams and subtract them from the diagrams on the previous slide. Okay, so I'm going to take the number of stars that fall in this bin in the north and subtract it from the number of stars that fall in the symmetric bin in the south. Okay? Now, if the galaxy is symmetric, if there's the same number of stars in the north as you see in the south, what should you see? It should just be flat, right? Just a gray, a flat diagram. And now I'm going to show you what you actually see when you subtract them. Call these the skunk plots, because they look like skunks. Skunks all the way. So in every single one, there's a white band and gray and white and gray. White and gray and white and gray. And what does this mean? Everywhere where you see a white main sequence, it means there are more stars in the north. And where you see a darker one, it means there are more in the south. And then more in the north, and then more in the south. And you see this in every single panel. It doesn't matter which direction along the galactic plane that you look, you see the same thing. And what we believe that means is that when you're looking at this distance away, where all the stars are about the same distance, but closer than the stars that are below it, the disk of the Milky Way is a little higher. So the whole thing is moved higher, and you see more stars in the north. And as you go farther away, and we're looking away from the center of the Milky Way, we're looking away from the center, as you go a little further away, there are more in the south. And then if you go a little bit further away than that, you see more in the north, and then more in the south. And so this is the plane of the Milky Way being perturbed up, and then down, and then up, and then down. So that's the main result. Now if we try to figure out how far away each of these dips or corrugations in the Milky Way is, we find that the nearest one, the first one where it goes up, is about 2 kiloparsecs away. We call that the near north. And then the next one is a little further away. This one is like 6 kiloparsecs away, and that's the south one. And then you see the one in the north over here, and the one in the south over here. And the one thing that I want you to notice in this plot, we've kind of picked points that are on the ring. Let's just look at this one here, the monoceros ring. We have the center of the galaxy here, and the sun is here. We're looking away from the center of the galaxy. And we see that in this direction, the monoceros ring is a little bit closer to the galactic center than it is over here. And the black circle is centered on the galactic center. And it gets a little bit further away as you go over here. And you see the same thing in Triangle and Andromeda. It gets a little bit further as you go over here. Same thing with the south middle. It's a little further. The near north is too close for us to get that kind of to make that kind of a measurement for more technical reasons. But it turns out that the spiral arms of the Milky Way follow about those same directions. The spiral arms are about in similar places, and they open out about the same way as these do. So we wonder if there's a connection between whatever causes these waves in the disk and what causes the spiral structure. But that's still to be determined. Okay? So in conclusion, we find an asymmetry in the disk that oscillates from north to south to north to south. That was the thing I said at the beginning. This near north structure is about 10.5 kiloparsecs from the galactic center, and it's about 70 parsecs, which is a significant fraction of the thickness of the thin disk. Above the plane, you have to perturb it up that much. And then the south middle is about 14 kiloparsecs from the galactic center, and it's about 170 parsecs below the plane. So you see that these wiggles are getting larger as you go out. And then the next oscillations coincide with the monoceros ring and the Triandromeda rings, and that they open in the same direction as the spiral arms. And that's the conclusions of the paper. But I wanted to put this in a little bit more astronomical context for you. What does it mean? One thing that it means is that the stellar disk is not falling off 15 kiloparsecs from the galactic center, or 50,000 light years. How does it usually go? Say 15. So yeah, 50,000 light years from the galactic center. It's not falling off. And if you look online or in textbooks, it'll say that the disk ends 15 kiloparsecs from the galactic center. And what we say is it doesn't end, it just shifts its position. So it looks like it's falling off when you're looking over it, but it actually just shifted to be in the south, and then it shifts back up, and you thought you saw the monoceros ring. But in fact, it's just still the disk going on. And so what we would say is that the stellar disk goes out at least 25 kiloparsecs, which is actually consistent with what people have seen looking at H1 gas in the disk of the Milky Way. So it's saying that the stars go out as far as the gas goes out. And if anyone measured the scale length of how much the density falls off in the disk, those numbers have to be revisited, because you have to understand that the disk is going up and down, and so these numbers would have to be revised. And then you ask the question, what could possibly be causing the disk to go up and down? And what we think could be causing it, and that's from other papers that have been in the literature in the last several years, is that there are dwarf galaxies, or possibly even dwarf galaxy-sized masses that don't have stars in them, so dark matter, that are passing through the disk, and just like a pebble hitting the water, you know, little waves will be induced in the disk from this mass passing through it. And so that sets up an oscillation pattern in the disk. And so in fact, you could imagine using the disk oscillations to try to detect dark blobs or ripples or dwarf galaxies that have gone through and made those ripples. Okay? And the last thing is it's possible even that the spiral structure of the Milky Way could be driven by that process itself. This is an artist's conception of the Milky Way. We don't have any actual pictures of the Milky Way because we are in it. But this picture shows you that there's these spiral structures, and if you try to set up a spiral density wave, something that will compress the gas and cause star formation along the spiral arms, because the star formation is what makes those bright. You set that up, you set up this wave pattern, the waves will propagate, and they'll die out in time. And it's unknown at this time what the energy source is that keeps those waves going. And it's possible that if there are satellites that are circling the Milky Way and going through the disk, that these satellites could be providing the energy or stirring the pot to make these spiral arms. This is a picture, it's a simulation done by the Aquarius project of a galaxy in the universe, in their simulated universe, that was made from starting with the primordial oscillations of density in the beginning of the universe and having time go on and have those oscillations grow and grow and grow until you've formed Milky Way-sized things. And when they form these in their simulations, they find thousands and thousands of what they call these subhalos, which look like little dwarf galaxies that would be in orbit around the larger Milky Way-sized galaxy. But when we look out in the universe, we don't see thousands and thousands of dwarf galaxies around the Milky Way. We see dozens of dwarf galaxies around the Milky Way. And so we don't know whether these exist, but they're dark and they don't have any stars in them, or if they don't exist and the simulation doesn't have all the physics of the universe in it. But you could imagine that if these do exist, then they're orbiting around, and some of them would be in orbits that would pass through the disk, and that they might, if they're large enough, you have to have a large one, they might excite these waves in the disk. So that's what we're talking about using galactoseismology. And there are papers that have predicted this in the past. Kazantzidis in 2008 and Younger, also 2008, suggested that if you have a dwarf galaxy and it passes through the disk, that it could excite waves somewhat like the waves that we're seeing. There's another interesting paper, Chakrabarty and Blitz from 2009, that suggested that from seeing the oscillations in the gas in the disk, that could have been another dwarf galaxy or subhalo, so dark or light satellite of the Milky Way that perturbed the gas that's seen in the disk, and that's very far out in the Milky Way. In fact, recently they, I think they may have found a galaxy that a dwarf galaxy that could have caused that, but that's a very new result. I have a movie that was made by Purcell. It's not liking that. And it doesn't play well in my PowerPoint, so I'm playing it here. So you have a Sagittarius dwarf galaxy. We know that there's a Sagittarius dwarf galaxy. There's one that's been observed. And it's in orbit around the Milky Way. It takes like 500 million years to go around. But it goes around, and it passes actually through the disk. Actually, right now it's about ready to start going through the disk. And that galaxy going around, as you see in this simulation, is having an effect on the mass that's in the disk, and it starts to cause oscillations and spiral-looking ring-like structures just from the effect of a satellite on the disk. And so this is what we're talking about, of having the disk perturbed by satellites going through. I have another movie which does play in the PowerPoint, so I'll put that up. And this one is a satellite that is a simulated satellite going through M31, which is our nearest large galactic neighbor, and that they found the same thing, that you send this little satellite here through the disk of M31, and it can cause the spiral structure that we see in that galaxy. Here comes, somewhere here comes the satellite. And even just getting, whoops, there it went through the disk. And when it goes through the disk, you get this pattern. So the simulations are showing that this kind of phenomenon is happening. And what our observations are telling us is that the disk is going up and down, which is consistent with that picture that we have a Milky Way galaxy that is far from being static. There are things that are in orbit around it. These things go through the disk. When they go through the disk, they disturb the disk, and they set up these wave patterns. And so that's what I wanted to tell you.